see the title here, Classical and Quantum Reality and the Collapse of the Wave Function. I want to talk about how, first of all, how the quantum state evolves. Well, normally we think about it as evolving according to the Schrödinger equation, but that doesn't tell us how the world behaves. We have to supplement that by, from time to time, the collapse of the wave function. And this is usually often not accepted as a sort of law of evolution of the world. But on the other hand, that's what we do when we try and make quantum mechanics concur with what actually happens in the world. The Schrödinger equation is a smooth deterministic equation, whereas the collapse of the wave function seems to be sort of happens suddenly. No, we don't really understand what's going on, but it's not deterministic as far as we can make out. Okay, I want to mention fundamental principle of quantum mechanics is the principle of superposition. And so if A is a quantum state and B is a quantum state, then we also have allowable quantum states by forming linear combinations alpha A plus beta B, where alpha and beta are complex numbers, not both zero. We're really interested in the ratio between alpha and beta rather than alpha and beta individually. Now, this is illustrated most beautifully in the case of spin of a spin-half particle, where we think of the different possible states of spin as being different directions in space. So they're points on the sphere, and we can relate that to the amplitudes. If we've got, say, spin up, that means rotating right-handed about the up direction, and spin down, and those are two orthogonal possibilities. Then W up plus Z down gives you, say, another state where you can see where it is. You take the ratio W over Z and you put the ratio as a point on the complex plane, and then you stereographically project from the South Pole, and the direction out from the origin to that point gives us the direction in which the axis of the spin is. So you can see a clear geometrical connection between the complex amplitudes and the directions in space, which is always, I found that really beautiful the way that works, particularly for a spin-half particle. Now, what about the basic principle of general relativity? Well, that is the principle of equivalence, which goes back to Galileo, of course, where at the top left we see Galileo, or his imagining himself, dropping a big rock and a little rock. They fall together so that an insect sitting on the big rock looking at the little rock would seem to feel as though gravity has been cancelled out. So that's the point. Locally, you can cancel gravity out. And at the bottom, I say, well, of course, nowadays it's very familiar, but you see here, this is a sort of 2001 fictional space station. Doesn't look like that, the actual one. Never mind. And the astronaut more or less hovers as though they're in the Earth right there. You can see the Earth there, but since they're both in orbit, pretty close to each other, you can cancel out gravity by simply falling freely with it. So that's the principle of equivalent. And of course, you have to have this wonderful theory of general relativity, because if you cancelled it out at Pisa, that doesn't cancel it out in New York. So you have to have a theory which accommodates this principle of equivalence all over the whole universe, which is what Einstein achieved in doing with his wonderful theory. Okay, now we've got these two principles, and I want to argue that there is a certain conflict between them. Now I'm imagining here an experiment done on a tabletop. This is a thing I put forward decades ago, but never mind, let's repeat the idea here. You're thinking of a quantum experiment done on a tabletop, and you want to take the Earth's gravitational field into consideration, just considering it as a constant field. Now, there are two ways you could do it. If you're any sensible quantum mechanic person, you would put a term in the Hamiltonian to accommodate the Earth's gravitational field. However, you might say, well, we should really do it in accordance with Einstein or Galileo-Einstein equivalence principle, and you consider a freely falling frame in which there is no gravitational field. And you have the two different colored coordinates. I think the green one is the one taken with respect to the table. the one static with regard to the table, and the purple one is the one where you consider the Earth's field. You're dropping freely in the field, and so the gravitational field is cancelled out. So in the green one, you see the gravitational field, and the purple one, you don't. Just do a little bit of a calculation, and what you find is that you get almost the same answer. The trick, however, or the key to what I'm saying is in the almost. What you find is that doing it by the green coordinates, that's the sort of Newtonian coordinates, or the purple ones, that's the Einsteinian way, you get a phase factor between the two. You might say, well, it's just a phase factor. Who cares about a phase factor? If you're working out probabilities, you're going to take the square of the modulus, and so you don't see the phase factor. But you should look carefully at this phase factor, because you see it involves the time cubed, an exponential of the time cubed. So it's rather a different phase factor. You could say, who cares about the phase factor? But you do have to care about it, because what it's telling you, because it's got a nonlinear term in the time, is that you actually have two different vacua. So the purple vacuum and the green vacuum are not the same. But you could say, well, stick to your vacuum and you get the same answer. Okay, well, that's fine. However, let's suppose I slightly modify this experiment by considering that as part of the experiment, you have a body which is put into a superposition of two locations, this body being sizable, and you're concerned with its gravitational field as well as the Earth's gravitational field. And you try to adopt the Newtonian perspective doesn't give you any problem, but you try to adopt the Einsteinian perspective, and you have a bit of trouble, because as you move around, you find that you can't sort of cancel out the gravitational field because it's in superposition. So how do you fall freely with it? And you can't sort of do that consistently all over space. So the point of view I adopt is say, well, okay, it's a bit of a mistake not to adopt the Einsteinian view, but let's do our best and just say that there is a little bit of an error involved and in not adopting the Einsteinian view. And then you can integrate this error over space and do an integration by parts. And you find what it is. It's a sort of uncertainty. I'm putting it as an uncertainty, not an error really. A little bit of an uncertainty in the total energy of the system. That's in the bottom right-hand corner. This is what you find. It's the integral of the square of the difference between the two different gravitational fields as you go around. And this energy turns out to be the gravitational self-energy of the difference between these two mass distributions in superposition. And I adopt the Heisenberg time energy uncertainty principle. So we've got an energy uncertainty that's related to a time uncertainty, well, a lifetime basically of the state. If it was like an unstable particle with a lifetime, then you would have an energy uncertainty, which is related to the lifetime by reciprocal relationship, and which is the Heisenberg time energy uncertainty relation. So I am adopting that viewpoint, and so that gives me a lifetime for the state, which depends upon the gravitational self-energy of the difference between the two states. This idea was actually not the idea, not my way of doing it, but the same formula had been come across quite a couple of years or so before I did it by Dioschi. So Dioschi had a different reasoning for it, but on the other hand, he came to the same kind of conclusion that there was this lifetime which you could calculate, which is this. Well, another way of stating it is if you imagine the two bodies, I think I've got this on the next one here. You can imagine the two bodies, it's not quite centered, but I hope you can see it, most of it anyway. The body, sorry, not two bodies, one body in two different locations, and the energy Eg, which is this gravitational uncertainty, you can either think of it as the gravitational self-energy of the difference between the gravitational fields of the two locations, or another way sort of you can think of it, as long as it's just a rigid displacement of one with the other, you can imagine pulling one away from the other. So these are the two realizations of the same object, pull it away from itself into the two locations, and how much energy did that cost you? It's just a sort of translational motion of one to the other. How much energy does that cost you if you're considering only the gravitational force between the two, which of course is normally very tiny, but nevertheless it could be significant if you've got big objects. If you pour one against the other into their superposed location, and you're concerned with the energy it would cost you to pull one away from the other, if you're just interested in the gravitational attraction between one and the other. And that's this thing EG all over again. So that gives you the same energy uncertainty, which I regard as the lifetime when you take its reciprocal, you take H cross over one and you get the other. Now, here we have a space-time picture. I'm adopting the so-called Penrose lifetime. As I said, Dioschi had it first. It's the same criterion as he was using, with perhaps a different motivation, but never mind about that. Here we have a space-time picture of a body. You see the bottom, the time is moving up the picture. So initially the body is in one location, and then gradually you pull it apart from itself. So it's now in a superposition of two locations until you get to the point where it's supposed to reduce from one to one or the other. Now let's suppose it reduces itself to the point Q star as opposed to the point Q in this picture. And so its reality becomes entirely at Q star afterwards. But you see, when does this happen? Now, it depends on which frame you look at it. I have two possible observer frames, the one with S, one with 1 and the other with a 0. And the S0 or T0 is the initial start. And then as time progresses, you have the simultaneity lines representing S1 and T1, and they're not the same. And here I have the picture where, according to the observer T, the disappearance of the particle in the right-hand location Q means that the object still hasn't yet become entirely at Q star. So somehow there's still a probability that it might disappear from Q star, which doesn't make any sense. If it's gone from Q, it's got to have gone from Q star. But does that happen instantaneously? That's not relativistic, because these different observers, one of them would see that the Q disappears before Q star is the whole state. The other one takes the view that Q star has become the whole state before Q has disappeared. And so there's still a chance that Q might be the state, and then you would get two examples all at once. It doesn't make any sense. The point is that the collapse of the wave function in this picture is not relativistic. So how do you make it relativistic? Well, pretty well the only way you can do it is to say, well, it goes all the way back to the beginning. That is at the location of Q0, point 0, and that's where the separation actually happened. So even though it took from the point where 0 up to the later time Q, that when the collapse has happened, it's as though it has happened all the time from O. So this rather curious picture. It's as though retroactively somehow, although the time scale tells you that it collapses much later, you have to make it relativistically invariant. It's a bit hard to make this make sense. And this, it goes back to the point 0. You can do it thinking about some kind of point of view where there is the alpha and the betas don't have to be normalized. That's the coefficient representing how much of it is at Q and how much at Q star, and that somehow there is a sort of one of them builds up and the other one disappears, and you might say after a certain point, you might as well say it one place or the other. It doesn't really make too much sense when you look at it in detail. To make it relativistically invariant is a real challenge. And so I'm saying, let's adopt that challenge. And what do? We say it goes back to the point O. Well, this is a point of view, and I want to distinguish between two possible points of view. And this is what I really want to talk about here, is what I'm calling quantum reality. Now, quantum reality depends on what I'm calling Einstein's dictum. And he was saying if without disturbing the system, I can make a measurement on the system, and with certainty, it tells you that the thing is either at one location or the other, something like that, but then that gives it an element of reality. So if you can make a measurement which doesn't disturb the system, then the result of the measurement is something real about it. So this is his point of view. He put this forward at least in 1935, perhaps earlier. And I'm calling this Einstein's dictum. Einstein's dictum is really a dictum which refers to what I'm calling quantum reality. So when we go back to here, this is a good example, the spin half particle of a quantum reality. You see this, you might have a situation where the spin state happens to be in some direction out from O to, in the top picture, from O to U, for example, so it's some direction. And that direction will be a linear combination of up and down, but maybe that is the real state. For some reason, you don't do some experiment and you could know that it should be pointing, the spin axis should be pointing in the direction out to the point U. And that gives the direction of spin an element of quantum reality. Now, it's not an element of classical reality, and I want to distinguish between these notions. And let me come to that. What do I mean by classical reality as opposed to quantum reality? Well, classical reality is something where you can ask a system, you can say, hello system, what is your state? And you could take some object. So I can take my magnifying glass here. I can say, what shape are you? And it says, okay, well, I've got a sort of round top, and then I've got a length here, which is about 4 times the diameter of the top. And it's fairly cylindrical in shape, a little bit of a kink in it here and there. Okay, it can describe what it's like. So that is classical reality. It's sort of fixed in this definite way. You can ask it what it is, and it can tell you what it is. It says, my state is X. So that's classical reality. Quantum reality, you can't do that. Like the spin half particle, it's a very good example of that. You can't say, hello state, what is your state? It doesn't answer that kind of question. No, you've got to have a clear state. You say, is your state X by any chance? If you've got it right, then it will say, yes, my state is X, with certainty. So you repeat this experiment many, many times. Every time, if the setup is exactly the same, every time it will say, yes, my state is X. However, if you don't have it right, maybe you've got a little bit wrong, then maybe 80% of the time it will say yes, and 20% of the time it will say no. You might have it nearly right, but not quite right. But you're not going to be able to tell. You can't ask it what its state. You can confirm what your belief is, and if your belief is right, that gives you the kind of reality. So I'm agreeing with Einstein. It is a kind of reality, but it has to be distinguished from the classical reality. Classical reality is a much firmer kind of reality. It's a much more sort of rigid thing which you can't monkey with. It's really knows what it's doing, if you like. Whereas the quantum reality doesn't, well, it sort of knows what it's doing, but you can't find out what it's doing. It's a very mysterious kind of concept, but nevertheless, that's the way quantum reality seems to behave. Now here I have a picture, which is a sort of space-time picture where I'm trying to illustrate both the quantum and the classical reality. And at the bottom of the picture, it's a sort of space and time mixed up in the picture, but time is really up the picture, sloping off slightly to the right, if you like, doesn't matter. Since we're talking a relativistic picture, that doesn't matter. At the bottom, I'm imagining a laser emitting a high-energy photon. This photon encounters a beam splitter, or half-silvered mirror or something, which means that the state of that photon is a superposition of being transmitted horizontally and being reflected vertically downwards. If it's transmitted vertically, it hits a lump of material. It's a very high-energy photon, so it gives it a good whack. And as we move up the picture, now that's time evolving, it takes a little while starting to move away from itself. You see that little body, the little grain of sand or something, which the photon has hit. is put into a superposition of being two locations in the quantum reality, because it's either hit or not hit, but it's not that. It's in a superposition of being hit and not hit. So that means the superposition of being moved and not moved. And as you move up the picture, you see this superposition grows with time, until, according to the Diochy criterion, you say there's a good chance that it will have become one or the other. You don't know exactly when it will become one or the other. It's, as I say, like a unstable nucleus. It's got a lifetime, but it does it's got a half-life, roughly speaking, which you can calculate from this formula, more or less. And in this particular case, when you go and look at it, or whatever it is, or by the Diochy criterion, it will have become one or the other. And that is the quantum reality state will be the superposition until it becomes one or the other. And then the classical reality has to go back to, you see, I'm having a picture of the curved space-time at the same time in this picture. The space-time has got slightly curved by the presence of that little grain of sand. And as it's put into one location or the other, it means the space-time is in a location of one or the other. But after a while, you have to say, no, the space-time is determined. It's one branch and not the other. And this means that the space-time, being a classical reality thing, goes back to the origin of the bifurcation of these two possibilities. So that is the picture I have. I was also trying to illustrate something else, which I'm not really the topic of this meeting, but it has relation to the idea of when consciousness happens. I'm not concerned with that issue here, but the idea is that also has to do with the interplay between classical and quantum reality. Let me continue and talk about the next picture, which I regard as a rather nice illustration of how quantum reality seems to work. This is a Bohm version of an Einstein-Podolsky-Rosen and EPR experiment. When I say a Bohm version, it's about a spin-half particle or two spin-half particles. Time is going up the picture, so we have a classical picture of time going up the picture. And there's Alice and Bob. Alice is represented by the left-hand line, and the right-hand vertical line is Bob. They're at the same place originally. They have a spin zero state, which is split into two spin half states, and they're put into a little box. Each one has this box, which is very well shielded from the outside world. And so Alice has a spin half state, and Bob has a half spin half state. And the state is the pair of the two, represented by the zero in direct brackets right at the bottom. And it still is represented as you move up the picture in that spin half zero entangled state. Alice and Bob don't have the whole state. The state is shared between the two of them. Okay, Alice makes a measurement at the point. You can see a spot there, QA. That's Alice, and Bob has a point, QB, and they independently make measurements. Let's suppose that Alice makes a measurement on her spin half particle, and she measures the measurement up and down, up or down, and she happens to find in this example that it's down, I think, isn't that right? I think that's what we're saying. Sorry, she measures it as an angle. I'm sorry, I got it wrong. She measures it as an angle, say 45 degrees, tilted to the right. That's that little arrow you follow up her world line, and you see up like that. And she sees that it's the direction of spin is in fact pointing up to the left. Now, Bob is independently doing a measurement, and he makes a measurement up or down. Now what is the quantum reality of the state? You see, because the quantum reality is supposed to be an objective thing, and it doesn't depend on the observer's state of mind. The observer could, I'm thinking of an objective observer who happens to be not actually an observer, it's really a way of looking at the picture. And how do you describe this picture according to a moving frame? That's really what I'm doing. And if you can think of a moving frame which could be moving very fast to the right or to the left, and to make this consistent, you have to say that Alice makes the measurement and she finds it's, I have to look at my picture. No, she finds that it's down to the left, isn't it? Down to the left, I think that's right, because she measures it up to the right and she finds the answer no, therefore it's down to the left. That means Bob's state is up to the right, and this happens, if you like, projected backwards in time along the past light cone to the point QB. So as Alice measured it at the top left-hand point, then you have to say that the quantum reality of Bob's measurement goes way back to B, because you might say he might have made a measurement at that point to test what Alice had done, and it's got to be consistent with it being the opposite of what Alice has done, if he happened to make that measurement. So you could say if he chose that, he would get a certain answer that it was the opposite of Alice's measurement. So that gives it a quantum reality of being that. Where she doesn't choose to make the measurement, and not much later, till the point right up at the top right, which is when he makes the measurement, and he chooses up and down. That makes quantum reality goes back to along the past light cone. And here I've sort of put in all the different areas where the quantum reality can be determined, right between the two sloping lines right at the bottom. You can see the quantum reality has to be this entangled state. When Alice makes her measurement, then the quantum reality goes back along her past light cone, influences Bob's quantum reality of his state. You see, he can't, why you don't have a contradiction with relativity is because quantum reality, you can't ask the state what its state is. You can just test whether you've got it right. And Bob doesn't know how to test whether it's right because he doesn't know what it is. You might get a signal from Alice later on, but that would be much later. That would be a signal which you'd have to, much later would he actually know what it was. But since he doesn't know, he can just probe the state himself, and you can imagine doing this situation many times, and you can work out what the quantum reality is. Anyway, it's quite intriguing that you do have a completely consistent quantum reality. I've only done it with this example. I don't know, with a much more complicated example, whether it's still consistent. I have no reason to believe that it wouldn't be. I think it's consistent. The only trouble would come if you could somehow ask the state what it was, what its quantum reality state is. That's the whole point about quantum reality. You can't do that. You can only confirm if you've got it right. If you've guessed right, or if you have a theory which tells you what it should be, and you test this theory, and if that theory is a good theory which tells you what it should be in this particular example, then you will get the answer yes with certainty. But in this particular example, that you can't do that, because all of the information is that what Bob or Mary Alice or Bob have made, and their measurements occur at different moments, and the quantum reality of that goes backwards along the past light cone, and you can fill in with these different places what the quantum reality is, and it seems to be completely consistent. Well, I think that's all I want to say for the moment. Thank you very much.